Okay, so here we are. We're continuing with section 8.7. All right, I'm going to do two problems here. The first, I want to find the integral from 1 to infinity of 1 over x squared dx. So this is one of the ones that we just had on the board. I'm going to be evaluating the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. That allows me to evaluate this integral. I get negative 1 over x evaluated from 1 to b. So I get negative 1 over b minus, if I plug in 1, I get a negative 1, so minus a negative 1. So and now if I evaluate that as b goes to infinity, that first fraction goes to 0 because we're dividing by that very large number, and plus 1. So I end up with a limit of plus 1. So this one converges, and it ends up equaling 1. This next one is big and messy. I want the integral from negative infinity to infinity of dx over 1 plus x squared. So the first thing I did was I split it into two integrals, from negative infinity to 0 and from 0 to infinity. 0 seems like a good place to split this. You know, though, if we got later into this problem and decided 0 was a lousy place to split it, there's maybe a better choice. It wouldn't be any work at all to change where we were splitting it. So now that I have these set up with negative infinity to 0, 0 to infinity, I can set up my two limits. The limit is a goes to negative infinity of a to 0, and the limit is b goes to infinity of 0 to b. So the antiderivative of 1 over 1 plus x squared is tangent inverse of x. So you can see that the limit is a goes to negative infinity of tangent inverse of x from a to 0, and the limit as b goes to infinity from 0 to b. So then I plug in all those values. And then some nice stuff happens. Tangent inverse of 0 is just 0. So both of those pieces turn into 0. And as a goes to negative infinity, the limit of tangent inverse as a goes to negative infinity is negative pi over 2. So I get a minus a negative pi over 2. And as b goes to infinity, the limit of tangent inverse as b goes to infinity is going to be positive pi over 2. So what do I end up with? I end up with positive pi over 2 plus pi over 2, which is just pi. All right, let's keep going. Let's get some more. All right, so next we want to ask the question, when does this integral converge? The integral from 1 to x of dx over x to the p, where p is some constant. So we're going to evaluate this integral, and then when we get to the end, we'll see if we can make a determination about what needs to happen for this to actually converge to a number. So this integral is equal to the limit as b goes to infinity of the integral from 1 to b of dx over x to the p. And that, remember p is a constant here, is going to be equal to the limit as b goes to infinity of x to the negative p plus 1 all over negative p plus 1. Keep in mind, to integrate this, you probably write it as x to the negative p, you add 1, and then you divide by that new exponent. And that's evaluated from 1 to b. Cleaning that up a little bit, I pulled out the denominator. I could have come further, and you can see I did on the next step. I pulled out that denominator because really all I'm interested in, this is just a constant. Whatever p is, 1 over 1 minus that is just going to be a number. So I'm really looking at this x to the negative p plus 1 evaluated from 1 to b. If I plug in b and 1, again, remember for x, not for p is our constant, I get, there's my 1 over 1 minus p limit, b goes to infinity, I get b to the negative p plus 1, and I get minus 1 because if you plug in 1, yeah, you get 1 because 1 to any power is 1. Whew, brain froze up there for a second. All right, so then I rewrote this b to the negative p plus 1 as 1 over b to the p minus 1. Remember, I just use a negative to bring it down to the bottom of the fraction, so that's why these both change signs. And that then gets us someplace we can work with. Minus 1 is just a number, that's no big deal. But what happens here? If p is greater than 1, this piece goes to 0. Okay? And if that piece goes to 0, then we just get the limit of negative 1, and so this is going to converge. But if p is less than 1, then we have a problem. If p is smaller than 1, then b to the p minus 1 power is going to end up going to infinity, which is going to make it diverge. So there we have it. This will converge if p is greater than 1, and it diverges if p is less than 1. All right, and of course, if it's just the first power, then it's a natural log function, and that's not going to converge. All right, so let's keep going. Let's try that again. All right, so now we're going to look at vertical asymptotes. Let's start with this example, the integral from 0 to 1 of 1 over the square root of x dx. As we can see, it has this tail here along the vertical asymptote where the area just seems to go on forever. So the question is, does this limit actually exist? Or, I mean, does this integral exist? Can we figure out what it is? So what we're going to do is we're going to have an a value. We're going to shove it towards 0. We're going to take the limit as this a goes to 0 from the right, and for the integral of a to 1 over the square root of x dx. So that's the limit as a goes to 0 from the right of 2 square roots of x. I'll let you do the integration, and then we're going to plug in a and 1. So plugging in 1 and a, we get the limit as a goes to 0 from the right of 2 times the square root of 1 minus 2 times the square root of a. But 2 times the square root of a is a goes to 0 is just 0. That limit does exist from the right. So we just end up with a limit of 2. So what we can say is, if we have a discontinuity at the beginning of our integral, vertical asymptote there, we can evaluate the limit as c goes to a from the right of c to b. And if the discontinuity is at the top, we just evaluate the limit c goes to b from the left of a to c f of x dx. All right, let's look at some more. All right, so let's look at this integral. The integral from 0 to 1 of 4r cubed dr all over the square root of 1 minus 4r to the square root of 1 minus r to the fourth. Now we have a discontinuity when r is 1, right? If you plug in 1 here, the bottom blows up, so we can't do that. So we're gonna integrate this. We're gonna use some substitution. Let's let u be r to the fourth. Then du is 4r cubed dr, and substituting for the variable limits of integration, we have if r is 0, so is u, and if r is 1, so is u. So we can change this to the integral from 0 to 1 of just du over the square root of 1 minus u. All right, so now let's deal with that 1 because it's still problematic. We're going to take the limit as a approaches 1 from the left of 0 to a of du over the square root of 1 minus u. And now we can integrate that. We get negative 2 square root of 1 minus u evaluated at a and 0. We can plug in a and 0, and then nice stuff happens. If a goes to 1 from the left, this square root right here is going to drop out because that goes to 0. 1 minus 1 is 0. So we can evaluate that limit very nicely. And this one is just 2, so we get that this very nicely converges to 2. All right, now we have some tests for convergence. We're going to start with what's called the direct comparison test, where we have two functions, f and g. They're continuous from some number a to infinity. And it's also true that they're both positive, and f is sandwiched in between 0 and g. So 1, if the big one, if g of x, if that integral converges, so does the smaller one. Okay, guaranteed. If g of x is always bigger than f, it's impossible for f to end up infinite if g is not. And the converse is also true. If the small one diverges, then since the other one's bigger, it's certainly going to diverge. So if the integral from a to infinity of f of x dx diverges, so does the integral from a to infinity of g of x dx. All right, don't worry, we've got more. All right, so we're going to do an example, and then we're going to look at the limit comparison test over here. So my example first is, let's look at the integral from 1 to infinity of cosine squared x over x squared dx. Now the key to this one is to recognize that cosine is always between -1 and +1, which means cosine squared has to be sandwiched between 0 and 1. That's important because then we can say that cosine squared divided by x squared has to be sandwiched in between 0 and 1 over x squared. Again, that's because we're working with values of x here that are bigger than 1, right? We're looking from 1 to infinity here. So this is going to be very nice. All right, so let's do this. So then what we can say is, we know this integral converges. The integral from 1 to infinity of 1 over x squared dx. It converges because p is bigger than 1. We had this earlier in the section, right? We found that if that exponent there is greater than 1, it always converges, and if it's less than 1, it always diverges. So this converges, which means by the direct comparison test, so does this guy, because that was the smaller function. All right, now for the limit comparison test. We have two positive functions f and g. They are continuous on the interval from a to infinity, and we know that their limit exists, that the limit as x goes to infinity of f of x over g of x is equal to L, whereas 0 is less than L is less than infinity. So it's equal to a number. Then either the integral from a to x f of x dx and the integral from a to x g of x both converge or both diverge. You can't have one of them that converges and one of them that does not. So let's look at an example here and see how this one might get put to use. Okay, so for our last example, we just want to know what the heck is going on with this integral. The integral from e to the e to infinity of the natural log of the natural log of x dx. Whew, that's a mess. So it's worth pointing out that I'm going to pull a substitution. I'm going to let x be e to the y, and its derivative then is e to the y dy. So when I do that, my natural log of x becomes natural log of e to the y, but natural log of e to the power is just the thing on the inside. So I get the natural log of y, and my dx turns into ey d to the y. So if I can evaluate this, definitely simpler looking integral will be in business. Except that this is still a mess. And so I want to try and evaluate this using one of my comparison tests. Turns out we're going to use direct comparison. We're just going to look at the natural log of y, because we know that natural log of y is sandwiched in between 0 and the natural log of y times e to the y, because y is bigger than e. All right. Whew, so let's see. What do we have? Well, since we're going to infinity, we have the limit as b goes to infinity and e to the b, natural log of y dy. Remember, we're working with this one. What we're going to find is that it diverges, and that's going to get us where we want to be. And that's equal to the limit as b goes to infinity. The antiderivative natural log of y is y, natural log of y minus y, and that's the value at b and e. So plugging those in, if you plug in e, natural log of e is just 1, so we have e minus e, so that part just dropped right out. So all I really have is b natural log of b minus b as b goes to infinity. But here's the thing, b natural log of b is going to infinity really fast. So yes it is. Which means that this whole limit is going to infinity. And so because the natural log of y is a smaller function this time, our function has to diverge by the direct comparison test. So there we go. Have a wonderful day.